All right, so here we are with 11.2, volume of prisms and cylinders. So our objective today is to learn and apply the formula for the volume of a prism and learn and apply the formula for a volume of a cylinder. Basically, the entire thing of this is finding the area of the base. So in a prism, that's going to be any shape that it is. In a cylinder, it will be a circle, and then multiply by the height. So the volume, here is our definition. It is a three-dimensional figure that is the number of non-overlapping cubes of a given size that will exactly fit in the interior, because we are talking about centimeters cubed or meters cubed as our unit, and so it's a bunch of these little cubes inside. There's Cavalier's principle, and Cavalier's principle has to do with this idea here. The idea is that you have either what they call a right prism, meaning it meets the ground or it's got perpendicular sides, or a oblique prism. And so the idea is that these actually have the same volume. It's just that one of them, even though they're the same height, one of them is slightly oblique or kind of shifted over, parallelogram kind of idea. And we know that a rectangle and a parallelogram have the same area. And so a right prism and an oblique prism are also going to have then the same volume. So that's Cavalier's principle. Just means that if it's leaning over, it's okay. It's still the same operation. So for the volume of the prism here, we have the volume of a prism with a base area. So notice that there's a capital B here. That's because we're talking about the base or what it's sitting on here, and then its total area being multiplied by the height. If you imagine a bunch of these triangles being stacked on top of each other, that's the idea. It's that many of that area and then for the height that it is. You'll also see here that there's the oblique prism, and the idea is that you are going to want to use the height and not necessarily the side length along the oblique prism. And so potentially you could have a right triangle in here that you might have to solve in order to get the height versus using that oblique side. All right, so here we are with a volume of a right rectangular prism. And so you've probably heard length, width, height. But of course, length and width are taking up this capital B here. And then you have your height. Same thing for a cube. It's a lot simpler than just doing your length or width and your height. It's side, but then that side length is cubed because you would have multiplied it 3 times. But again, if you don't remember these two formulas, you can always just go back to I just need the area of the base and then multiply by the height. All right. So taking a look at our first example here, we need to find the volume of a rectangular prism with the length of 12, a width of 10, and a height of 8. We haven't necessarily talked a lot about drawing three-dimensional figures yet. And so especially if you're looking at our images here, a lot of times the sides that are not necessarily or wouldn't be able to be seen if this wasn't see-through here are given in a dashed mark, okay? And so a lot of the times, again, the sides behind are dashed. All right. So we're going to find the volume of the rectangular prism, again, 12, 10, and 8. And so I could try to draw this here if I wanted to. I don't really need to draw the image, but it's nice to kind of practice. When you do that, the rectangle that you have, because you're trying to draw 3 dimensions on 2, tends to look more like a parallelogram on the top and bottom. These 3 sides are going to be visible if I was looking at this prism. But this side behind here exists but isn't necessarily visible. This side over here, again, dashed because it's going to be there but not visible. However, the front and this right side will be visible. And then again, this back side exists but again is not visible. So kind of got our cube here. And again, they said the length was 12 centimeters. The width was 10 centimeters, so not necessarily to scale. And then the height is 8 centimeters. So again, 2 ways that we can do this. We can follow this volume here, which says that the volume is length times width times height. Or noting that length and width is the area of the base, we could multiply that by the height. So either way that's happening, but I'm going to use length, width, and height. That's kind of what I learned when I was in school, so I go back to it. But length and width and height. So plugging those in, I'm going to get the length value, which is 12, the width value, which is 10, and the height value, which is 8, and I'll multiply all of those together. So 12 times 10 is 120, and then 120 times 8 is 960. Sorry. We are doing, centimeters as our unit, and then cubed because it's volume. That is our volume. All right, in the next example, we have a cube with an edge length of 10. So again, if you want to take the time to try to draw a cube, you're looking for a basically rhombus at the beginning here. And the more squished it is, the more you're looking at it from the side versus the top. So kind of interesting things to play around with as you might draw a cube. We've got our 3 legs. You want to make sure that those legs as you drop them down are the same length. And then each of these sides inside. So either way, we've got our cube and the edge length is 10 centimeters. So we can use those 2 formulas, again, potentially length, width, and height, because this is a rectangular prism as well. We could also use the area of the base times the height, or we could just use the fact that it's the side length cubed. So since it's a cube, I don't necessarily need to take the time to write out each of the pieces. So I like to use this one here where it said the side length is just cubed, because otherwise you start to look for more variables within here or numbers and you don't find any and then you get lost. So potentially that's 10 there and then also here and then here, but we don't necessarily need to write it in there that many times. All right, so then we take 10 and cube it, which means that we're going to have a 1 with 3 zeros behind it. And so 1,000 meters, centimeters, squeezing a C, cubed is going to be the volume of that. All right, and we did kind of play around with volume a little bit when we did our magic circle project. So you do remember, hopefully, that things need to be to the unit cubed when you're solving. All right, next example that we're going to do is a right regular pentagonal prism. Yikes. So all that means is that each of these side lengths, or each of these faces, meet at 90 degrees. That's the right idea here versus oblique. The regular means that each of these, and maybe it says it, no, each of these sides of the pentagon are all, in this case, 5 meters. And then it's a pentagon, so we got 5 sides, and then a prism. So that means that this pentagon here is repeated at the base, and it has rectangular sides. So kind of a long name for this, but there it is. And its base edge is 5 meters. They've mentioned that. And then the height there is 7 meters. So as much as you're thinking, oh, okay, well, the volume is the area of the base times the height. So I just need to take 5 and multiply it by 7. But of course, that's not what's working. 5 is the base edge, not the base area. And so we have to do quite a bit of work here to actually get the base area, which we will then plug in for B. So taking a side step to how we solve to get the area of this pentagon. So we have this pentagon here, which I will try to redraw nicely. Okay. And then we've got this measurement here, which remember is called the apothem. Okay. We also have that they've broken this into a right triangle here. And they've told us that this angle measure is 36 degrees. So we don't have to go through figuring out how to get that. And so if we take this and actually use the right triangle that they gave us, we're looking at 36 degrees up here, 5 meters, but actually it's 2.5 meters when it's just in this right triangle. And then we're trying to find the apothem. Again, the reason we're trying to find the apothem is because the area of the base is a half apothem times perimeter. And so we know that the apothem is what we're trying to find, but the perimeter is going to be 5 times the fact that there are 5 sides, so 25 meters. All right. So then continuing on with this is where our trig comes in. And so now we need to set up our trig problem. We have this angle here that we're going to call our theta, or talk about where we are standing over here. This is the opposite side to that theta, and this is the adjacent side. And so when we think of SOHCAHTOA, oops, I forgot the H in KAHTOA. Okay. We are looking for adjacent and opposite. So that means we're looking at T, which is tangent. And so I know that tangent of the theta value is going to equal the opposite side over the adjacent side. Or if I take the time to fill that in, I'm going to understand that tangent of theta, which is 36 degrees, is going to equal the opposite side, which is 2.5, over the adjacent side, which we're calling A. All right, so in order to solve this, tangent of 36 equals 2.5 over A. I'm gonna start working over here. Oh, that's 36. We're going to set this up as a proportion and go ahead and multiply 2.5 times 1. And then divide that result by tangent of 36. So again, A is going to equal 2.5 times 1, and all of that divided by tangent of 36, which is a decimal. So our apothem ends up being 0.5, divided by tangent of 36. If you're not in degree mode, that 36 is going to be assumed to be a radian, which is huge, so we don't want to do that. So we'll have 3.441 if we round 4 decimal places. So that means we're going to have a half times the apothem we just got, which is 3.4410, times the perimeter, which is 25. And so now we know the area of the base, or of this pentagon, is going to be that number times a half times 25. And so the area of the base is 43.0119. All right, so going back to the original equation, I know that my volume needs to be the area of the base, which we just found to be 43.0120. Oh, I rewrote that wrong. 119. That's gross. Okay. And then times the height, which they said in the initial problem here was H. 7. So 43.0119 times 7, sorry, that's so sloppy, is going to become our volume of 301 point, what does it say? No ideas of rounding, so 08. And our unit is meters and cubed because we're doing volume. So just as it was in our last section, finding the area of a pentagon or any polygon here is a little bit more difficult when it's more than 3 sides, or even more than 4 sides. So and remember that you are going to have to use the trig to find that apothem, and then once you find the apothem, it tends to work out from there. So that was number 3. The next idea is that the volume of a cylinder, as we talked about with Cavalier's principle over here, can be oblique or it can be a right cylinder. But either way, the volume is going to be the area of the base times the height. But what's special about a cylinder is, of course, the base is a circle. So we end up having pi r squared height instead of just area of the base times height. All right. So in this first example here, we need to find the volume of the cylinder. So this is going to be direct. They want you to find it in terms of pi, but then also rounded to the nearest tenth. So notice that it is oblique, and they do give us the height and not that side length. So in that case, we don't need to do any extra work to find out what that height is. It's already given. So I know that 12 is my height. 8 is actually the radius. And so when we look at the volume formula of pi r squared height, or of course pi r squared is the area of the base, which we could do as the formula as well, we're going to fill in pi times the radius, which in this case is 8. I'm just going to 8. 8 is going to be squared, and then we'll multiply that by the height, which we found out to be 12. All right, and remember that they want you to find this in terms of pi. So if we solve this first and then put it next to a pi, then that's going to be one of our answers. So 8 squared times 12 is 768. And of course, that's a little weird to look at, so we like to put the variable or the pi at the end. So one of them is 768 pi, and we are looking at centimeters cubed. But we could also actually take 768 and multiply by pi and get the number of 2,412.7, rounding to the nearest tenth, centimeters cubed. All right. There is our fourth example. Moving on to example 5. We need to find the volume of the cylinder with a base area of 36 pi inches squared and a height equal to twice the radius. So kind of one of those backwards problems where they're not just going to give you, as we got in the previous example, the radius and the height, and then you fill it in. We're going to have to work backwards. They're telling us that the area of this circle, which should be pi r squared, is equal to 36 pi. So if we go ahead and solve that to find out what the radius is, because we'll need that, if we divide both of the sides by pi, those cancel and you're left with r squared equals 36. And of course, square rooting a square will leave you with a radius of 6. So we know that the radius is 6, and then the height is equal to twice the radius. So if the radius is 6 and the height is double that, then the height has to be 12. So now we can find the volume because we are able to fill in, now that we have a radius and a height, pi r squared height with a radius of 6, which we will square, and a height of 12. It doesn't say anything about putting it in terms of pi, so we're just going to go ahead and multiply all of these across. So pi times 6 squared times 12 gives you a volume of 1,357.2, and we're using inches cubed. So that one started with an area, had you then find the radius and then therefore the height, and then plug it into the volume formula. All right, in example 6, we have an image here with a cylinder with a radius of 6 and a height of 12, and they're saying that the radius and the height of the cylinder are multiplied by a half, and we need to describe the effect on the volume. We did go over this a little bit in our last section, in our last chapter, when we talked about converting dimensions that have been changed. So in our last chapter, we kind of had this image of if we have a length, which could be a perimeter, or a width, or any other number of measurements, maybe a radius. What happens is this is one-dimensional, but if we want to convert to 2 dimensions, which is your area, or even 3 dimensions, which is volume, to get from 1 dimension to 2 dimensions, you need to say that you would have actually multiplied by whatever that multiplier is squared. So it turns out that to get from 1 dimension to 3 dimensions, you're going to multiply by that number cubed. But then, of course, if you wanted to actually go backwards and say, oh, well, the volume was multiplied by 3, what happened to the side length? Well, to get backwards, the opposite of something cubed is going to be cube rooted. Yes, you can have a third root of something. And then the backwards of having something squared would be the square root. Turns out that to get from the one to the next, you can also square. So again, you could say I'm going to square to get to here and then square again. Well, not actually, it's cubed to get here. So, all right, so that's just kind of a note from last chapter. So in this case, the radius and the height of the cylinder are multiplied by a half, and we need to describe the effect on the volume. And the idea that we are going to assume is that the volume will be multiplied by, because again, the height is length, and the radius is a length, and so we're going to take that half, and when we're talking about the volume, bring it to the cubed. So in that case, it's actually 1/8 that it's multiplied by. So again, this is our guess based on the knowledge here of cubing something to get from distance to volume. So in this case, we will actually find the volume. So this is the original volume. And the original volume is going to come from pi r squared height. The radius is 6, the height is 12, so pi 6 squared times 12. This is actually the same problem as what we had up here, so we know that our volume is 1,357.2 inches cubed. Only now they're using meters. But then we need to find the new volume. And so we need to take each of the pieces that we just had in pi r squared height and multiply each of them by a half. So we have our radius, which is 6, but then divide it by 2 or multiply by a half, which you will then want to square since that's your radius. And then a 12, but then again, that is going to be divided by 2 as well, because we're taking everything and multiplying by a half. All right. So that means that we're going to have pi 3 squared times 6. That's a 6. And so we're going to have pi times 9 times 6, or a new radius, a new volume of 169.65. So again, you're looking to see how did we get from 1,357.2 to 169.65. And I assume we multiplied by an eighth because that's what our guess was. So let's see if 1,357.2 times 1/8. Remember that multiplying by 1/8 is the same as dividing, but anyway, 169.65 is our answer. So this works. And so to get from the original volume to the new volume, if the lengths were all multiplied by a half, then the volume is multiplied by an eighth. All right, and then we have our last example. And this last example is about something called a composite figure. All that means is it's more than one shape together. So if we take a look at what's happening here, we actually have a cylinder on the top of a triangular prism. So all we have to do is find individually the triangular prism volume and then individually the cylinder volume and add them up together. So I'll put an extra E in cylinder. volume and prism volume. So in order to get our composite figure, we'll do our cylinder volume, which has a height of 5. They're also not having this cylinder go completely across this rectangular side, but you'll notice that it does go completely across this side here. So we would be able to find our diameter of this side if we know what this length is. And we can find that length because this triangle right here is a right triangle. And so we can just solve with the Pythagorean Theorem what the side length would be if that's 6 and 8, and that we don't know yet. So we can do 6 squared plus 8 squared equal to the hypotenuse squared, or 36 plus 64 equals c squared, or 100. And so that means that 10 is our c value. So that means that 10 meters is this length of that triangle, but it's also the diameter. And so that means the radius is 5. So if we're trying to find the cylinder volume, we need pi r squared height. We know that our radius that we just found is 5, and the height was given to be 5 as well. And so we have pi times 25 times 5. And so the volume of the cylinder is 392.6991. All right, then if we find the volume of this triangular pyramid, remember that means that we are trying to find the area of the base times height. Our area of our base is a half base times height of the triangle times the height of the prism. And so our base of this right triangle is 8. Our height of that right triangle is 6. So we're going to do a half times 8 times 6, but then times the height of the prism. So 9. Again, this is the height of the triangle, and this is the height of the prism. So we don't want to get those confused. So a half times 8 times 6 times 9 leaves us with 216 as our height. As our volume. So that means that the total volume is going to equal 392.6991 plus 216. And so the total volume, 392.6991, is going to be 608. Rounded to the nearest tenth, 0.7. And we're doing meters, and it's volume, so cubed. All right, so basically they're just trying to get you to do one problem, but of course 2 problems in one. And in fact 3, because we had to do the Pythagorean Theorem. So, all right, so that is our notes for 11.2, and so now you should be able to apply that to the assignment.